Okay, this question seemed to have been done quite well. The biggest problem people had was keeping things clear what you were trying to do. Most of you drew quite good diagrams to start with, so we've got the centre of a circle and it comes somewhat round. Point A, 30 degrees below the horizontal, and it was at point A it is projected with a speed u. It then gets to a point B 30 degrees above, and we've got to find the speed at the top here, so I'm going to call that V. I know a couple of people tried using energy equations for this, but as we don't know what U is at the moment and our answer is only in terms of R and G, unless it's going to cancel, we need to be looking for something else. And the fact that we need to find U a bit later indicates we probably need to think about something else. So those of you who tried the energy equations at this point probably had a bit of a problem, just simply because the equations really weren't thinking through what was happening. So let's draw the particle at B and see what's happening. There is in here a radial component force which comes from the reaction. So there's a reaction force here. We also have our speed V, reaction force, and the question and our mass gravity here, mg. So what we need to actually work out is we're still moving in a circle, so at this point one of the forces or the result of the forces is mv squared over r. That is equal to the reaction force plus the component of our gravity along this direction, which is going to be sine of 30 because that's a 30-degree angle inside. mg sine 30. Now the first thing to note is if we're on the point at B, it says it's on the point of leaving. So at B, R equals 0 because it's just leaving. So we now get our equation, mv squared over r equals mg sine 30 a half. Rearrange our equations and we get v squared equals 1/2 gr, and therefore we can square root both sides. And just getting that part isn't worth anything because we've been given it in this part of the question. It's given here because we need it in part B. Okay, so that was part A. Just make sure that we're clear what bit of the question we're answering. So part B we can now deal with in terms of energy. So energy at B must equal the energy at A, and that's the conservation of energy. Do state your principles, say what you're using. So if we look back at our diagram, the kinetic energy is 1/2 mu squared. Potential energy at this point, I'm going to take the potential energy above the point at, oh sorry, I got the wrong way around, that was it. That one should be A. That one should be B. Yeah, potential energy, if I take A as being the base at this point, so A is no height, there's no potential energy. So that's the kinetic energy at A. The potential energy at A, and we're now going to see what's the potential energy, kinetic energy at B. And that's half mv squared, declared and variable in my diagram, and the height, or the potential energy at B, is mg sine of 30. That's how far it is above the centre. If I'm taking A as being my potential energy, my base, I need 2 lots of it, because it's twice as far up. So now I can put in the bits I've worked out. I've got cancelled through by the m's and the halves. So I've got u squared is equal to v squared plus 4mg sine 30. Substitute the v from above, 1/2 gr. Half of that is 2mg. Oh, where's my m gone? I messed up the r from there. The r here is to give me my height, r here to give me my height. So we plus 2 gr. So u squared equals 5/2 of gr. And therefore u is the square root of both. And that's using conservation of energy to find out where the position B is. Now part C, which is about finding where does the particle go after that. So just after this point, what does it do? What's the maximum height? Now most of you actually did realise this bit, but this bit height here is r plus 1/2 r. And then we need to work out what the height is as it moves through the air, not touching the circle. There are 2 approaches. One is to use SUVAT, one is to use conservation of energy. Now I'm going to show you both because some people had problems with the conservation of energy. They forgot that when you do the conservation of energy formula, you need to include the horizontal component of your velocity. So if you haven't got a horizontal component up here, your energy equations don't balance out properly. So I'm going to do it in 2 ways. So let's go for method 1. So part C, using SUVAT. Draw a diagram at B again. We're moving at a velocity that way. This velocity v, which was in part A. That was another problem, is people kept mixing up which velocity was which. The angle that makes, if that was 30, that angle 60 degrees. So we can now calculate the vertical speed. So v vertical at this point is v dot sine of 60. So thinking about SUVAT, we know u, the flight velocity at the maximum height is 0. So we've got 2 velocities. It's acting under acceleration, is just gravity in the bottom direction, and we want the distance. So the SUVAT equation we're going to use is u squared, v squared equals u squared, add on to a s. And this s is the height above our point. So we've got a height here, x. It's above the point B to the maximum height. Okay. Put the bits in. So v squared is 1/2 gr. U squared is 5/2 gr. Oh, I forgot to do all those the wrong way around. So my velocity at the end is 0 squared. My vertical velocity is the velocity of v, so the half gr, times the sine, and that's square rooted, but we're going to square it in a minute, times the sine of 60. So this is actually technically square rooted and then squared, and the sine needs squaring to give me my velocity squared, minus 2 lots of gravity times my height. So when we rearrange the values, we've got 0 equals 1/2 of gr. Sine is root 3 over 2, so 3 over 4 minus 2gx. So I can rearrange my equation. I've got 3/8 of gr equals 2gx, so x equals 3/16 of r. The g's have cancelled out for me. So that, if we remember our original diagram, we now need to add to it a radius and half a radius. So the height above the bottom I don't think I put C on the diagram. So I forgot to put that part as C. So we've got 3/2 C of R plus the last answer. 3/2 of R plus 3/16 of R multiplied by 3 is 24, is 27 over 16 R. That's the method using silver. The alternative method, C using potential energy. Conservation of energy method. So we can take point A, need to remember A, and we're going to do conservation of energy above C. So the KE is 1/2 mu squared. Potential energy at A is plus m times g, and notice this is a radius and then down radius times sine of 30. And on the other side, at the top, the point X, max height, we have a kinetic energy which is 1/2 mv horizontal. That's the horizontal component as we leave B. And all following times. And my potential energy is going to be my mg and my height x, and the x is what I'm trying to work out. So we've got to work out the horizontal velocity at B. So we actually want this v there, angle 60 degrees, like I just did with SUVAP. Now for the v horizontal, that is v cos 30 or 60. So that is 1/2 of whatever v was. So now I can substitute that into my equations. 1/2 mu squared. U squared was part B, so 5 over 2. And this is why some people made mistakes. They made mistakes because they didn't bring together the correct U. That's U from part B. This is 1/2 of R, so plus 1/2 of mgr is equal to 1/2 of m times 1/2 of v all squared, so that's a quarter of v squared plus mgx. V squared horizontal. Oh yeah, I've got to substitute it. I didn't substitute in my v squared properly. V squared is the part we did in part 1, which is a half rg, or square rooted. The reason I realised was I wasn't getting the g's to cancel out, so I'm going to cancel out all the m and g's and simplify all my fractions. So I've got 5/4 of r plus a half of r is equal to 8/16 of r, and that is equal plus x. So if I rearrange, put everything into the common base, so that's going to be 20. Yeah, multiply that by 4 to give me over 16. You want a common denominator of 16. Yeah, multiply by 4, multiply by 8, and then subtract the 16th. All of those with a common r is x, and simplify the fraction. Gives me the same 27/16r that I got using Survat. Okay, so that's two methods for solving part C, which is where people had problems with this function.